Okay, so now let's write down an equation that describes propagation of a sound wave. So what we're going to consider, we're going to think about a gas. Now again, sound waves are applicable to any medium, and you can have a sound wave traveling through your wood desk, through water, through all kinds of things. But let's just keep the idea of a gas in mind as we derive it. We're going to consider the forces. We're going to write F equals ma, just like we did for the string. Okay. Um, so let's start with ma. So okay, we're going to write F equals ma. So ma equals F. We'll consider things to be one-dimensional. Consider, our gas. So we have some bit of gas. Let's just imagine we draw a box. So here's our gas. Okay. The box will have a size delta x in the x direction, and it'll have area A in the other two directions. Okay. And so we'll also define that the gas has a certain density. This is going to be, that's supposed to be a rho. Let me try again. Rho, which is a number of kilograms per meter cubed of air that's in there. Okay. Now, so the mass then is going to be A, the volume, which is A times delta x, times the number of kilograms per volume. And we're going to the acceleration of these particles. So if you remember in the previous video, I talked about the displacement of each atom in the gas, d. And so we're going to use that to describe the motion in the x direction, because these particles are going to be forced and move in the x direction. And so we're going to introduce this displacement function d, and the acceleration is just the second derivative of that displacement function. So this is equal to ma. This is our mass times acceleration. Okay, now the force is due to pressure. Okay, and as I said in the previous video, pressure is a kind of a special thing. It's not really a force on each particle. However, we can think about it that way. We can think about it, and not only think about it, we can mathematically analyze it in that way. Okay, so if we assume it's a force, let's take our same box of gas here. Okay, delta x, and this is A. Okay, now pressure, formally speaking, pressure is the force per unit area. Okay, that is due to this random thermal motion in the gas. So you can think about the force, the pressure acting on either side of this box. Now, pressure is like the opposite of tension. So in a rope that's under tension, each little bit of the rope feels a force both to the right and to the left, kind of stretching it out. So for a pressure force, you're being pushed on from either side. So you're being pushed on like this and like this. Okay? And so we want to find the net force on that body, that box, and that's going to be the difference in the pressure on either side. So let's call this location x1 and this location x2 here. Okay? And then the net force on this box is going to be the area times, because the pressure is force per unit area, times the pressure at x1, which is pushing to the right, minus the pressure at x2, because it's pushing to the left. Okay. Now I can rewrite this as the following. I have A times delta x times P at x1 minus P at x2 over delta x. Okay. All right, so let me now put those two components together. I have F, I have MA. Okay, if I put them together, what I get is A times delta x times rho times d squared d t squared. That's ma. And that's going to be equal to now A times delta x times the pressure at x1 minus the pressure at x2 over delta x. Okay, now what I'm going to do is take the limit where delta x goes to 0, and that's going to turn into a derivative. Okay, I'm going to cancel these first. So now I can get rid of the volume. That drops out. and then take a limit. Now really I've already taken a limit here because I just said let's use the acceleration as d squared dt squared, but that's assuming I'm at one point, okay? And of course in that box that I drew, the displacement's going to vary with position. So this is effectively already taking the limit where my box is small, okay? Now I'm going to do it over here, and this is going to turn into a derivative, and it turns out it's going to be the minus the derivative of pressure with position. Okay, and the reason it's minus is because we generally define the derivative to be positive for increasing in the positive x direction, right? So the way I've written it here, I have it backwards. I should do p at x2 minus p of x1 over delta x. That would be the positive derivative, okay? Excuse me. All right, so now my wave equation is rho d squared d dt squared equals minus dp dx. Okay, so I've got f equals ma, but now to turn this into an equation of one variable, I have to relate p to d. Okay, how are those two related? So we know that by compressing the gas, we increase the pressure. And we know that by displacing the gas molecules, it generates compression. But we're a couple steps removed from that. So let's talk about that. So we're going to use a couple of different relationships to do this. So first of all, I can relate the pressure to the density. Okay, this is this is something I can do physically, make a relationship between those two. And then what I'll do is connect the density to the displacement. Okay, so I'll do it in a two-step process. All right, so what we're going to consider is the wave perturbation on the pressure and the density. Okay, so we're going to write down that the pressure is going to be some background pressure plus some perturbation, and I'll call it delta P. Okay, or actually, rethink that. I went back and forth here. Let me just call it P wave. Okay, all right, and P wave is much smaller than P naught. Now, the reason for that will become clear in a second. And then we have a density, which is some background density in the air. And then as the wave goes by, I get a perturbation that I'll call rho w. Okay. All right. Now it turns out that we can imagine that the pressure is a function of the density, and we can expand it. So we can assume that the change in the density is small. Okay. So as a function of density, and we can expand this pressure about the mean density. So we can say this is going to be equal to P at rho naught, okay, plus, now we're doing a Taylor expansion. It's going to be the derivative of P with respect to rho, okay, evaluated at rho naught, times rho minus rho naught, okay, which is going to be this rho w. That's going to be the distance from rho naught, okay, and then I can keep going. Right, so this is a Taylor expansion. And the assumption I'm going to make is that rho w is small, right? So we'll make the same assumption we did with the wave on a string. We assume small perturbations. That's when you get a linear wave, okay? All right, and so we'll ignore all of this. And now if we look at this expression that we've written, this is really P naught. This is the pressure without the wave. And this is going to be PW, my perturbation due to the wave right here. Okay. All right, let's go to the next page. All right, and so we don't know what d PD rho is. That depends on the material. So if I have a piece of glass, the pressure in the glass will change differently as I compress it than if I have a piece of silly putty, right? And so it's going to depend on the material. And so what we can do is just use empirical measurements, okay, of that relationship between P and rho. And so usually we call this object the bulk modulus. Okay, so we relate the change in the density. So let me do this first. Okay, so based on what I said earlier, the pressure change due to the wave can be written as the density change due to the wave times dp d rho. And this is the thing we don't know. So we can just make a definition. And usually we write it this way. We introduce the following. We say that's equal to rho naught over rho w over rho naught times a coefficient called the bulk modulus b. So bulk modulus b over rho naught is exactly this derivative. And that's something you measure. You just go in and kind of squeeze the object a little bit. Really, you measure it with this kind of thing in mind. You say, okay, I squeeze the object, I change its density a little bit, and I measure how much the pressure changes. And then I write down that B, and that's the coefficient. That's the bulk modulus for this stuff. Okay. All right, so that's kind of a definition, really. We're assuming that the assumption we're making is that the pressure change is linear with the density change. That's what this expression is. But then we have this coefficient we just put in by measurement or ad hoc. Okay, so now we have a relationship between the pressure change due to the wave and the density change due to the wave. Now what we need next is a relationship between the density change in the wave and the displacement of the wave. Okay, so I'm not going to go through a rigorous derivation of this. Okay, but I'll just write it down and hope you believe me. But I'll try to motivate it. Let me do it this way. So I drew this kind of picture in the last video. If I have a sinusoidal wave and this is my displacement. Okay, I made the case that you're pushing particles. The displacement, if it's positive, it's pushing things to the right. So all these particles at these locations go to the right. These particles go to the left. And so where I'm going to build up a density and a pressure is right here. Okay? And if I look at this, this is at the location of maximum gradient in the displacement. Okay, that's where I'm going to really accumulate density. So a positive density will happen when the gradient is maximized, but it has not just any gradient, because in fact if I look over here and if I continue this wave, this is going to be, this will be a low density point because I'm going to lose particles to either side. So this also has a magnitude of the gradient big, but the difference is the sign. So when you have a positive slope, you get less density buildup. When you have a negative slope to D, you get a lot of density buildup. And it turns out you can write the density change due to the wave, okay, as the background density. I need a minus sign here, sorry. It's inversely proportional, well, negative of. So rho W is minus rho naught times d dx. Okay? All right, didn't derive it, but hopefully the picture above it makes sense to you that the bigger the gradient in the derivative in the displacement, sorry, the larger the buildup of excess density due to this displacement. Okay. All right, so this is the density due to the wave. All right, and so I've related, and now I can take it one step further. Let me just write it here. If I now look at I'll write it on the next page. Let's go to the next page. All right, next page. So now my equation, I have rho naught, and I've introduced the naught because I'm focusing on this is the bulk particles that I'm pushing with the wave. I'm not interested in the perturbation due to the wave. I'm interested in moving around the particles that are sitting there. And I have a minus dp dx. Now I can replace that with my bulk modulus. So if I assume the rho naught is uniform, when I plug in my bulk modulus over rho naught, now another point to make, this is the pressure due to the wave. Okay, now really it's the total pressure. However, I'm going to assume that P naught, the initial pressure, is uniform, and so it has no gradient, and that goes to 0. So the only thing left behind is the pressure due to the wave. That's what forces things to move. Okay, so I plug in my expression for the pressure of the wave. I get d rho w dx. Okay, and now one further step, I plug in my expression for rho, as a function of d, and then I get b, okay, times d squared d dx squared. The rho naughts cancel there. Okay. All right, and then one further step, I can rewrite this as d squared d dt squared minus b over rho naught d squared d dx squared. So now here's our wave equation. So this looks identical to, analogous, well, it's the same form as the wave on a string, but now my wave speed is different. So we call this speed, this is the speed squared, if you remember. So we call this the sound speed. And so the sound speed is b over rho naught. Okay, so like in the case of wave on a string, I have the restoring force on top, which is the bulk modulus, and the inertia, the density on the bottom. Okay, all right, and so we get waves that propagate at this speed. Okay, I want to say one more thing. Excuse me, getting a bit of a cold, I think. All right. We saw that the sound speed is written as root b over rho naught. Okay. In general, it's difficult to calculate what the bulk modulus is for a particular substance. In other words, if I squeeze it and compress it, how much restoring force is there? But for an ideal gas, we can't actually do that calculation. That's the simplest thing we know about. We can compute what the bulk modulus is if you compress a gas. Now, if you remember, you may have seen this before. The pressure of an ideal gas, that's the total pressure of the ideal gas, can be written as the number density, the number of particles per cubic meter, times Boltzmann's constant, times the temperature. Okay, you may have seen this as PV equals nRT before. It's the same expression. Okay. Now this is, again, the total pressure. What I'm interested in is the change in the pressure due to a compression, and that's a different thing. So when I compress the gas, I'm doing work on it, and that can give it energy, and that energy can go into heating the gas. And so I have to account for that process. Okay, so it turns out that if I compress the gas and look at the change in the pressure, not P total, but PW, the change in the pressure. So remember, the total pressure will be the background pressure that I start with, and then the change due to compressing it. Okay, and that's because I changed the density. So I go from, I have a background density, then I change it in some way. Okay, and then I get a pressure change. All right. In looking at a change in the pressure due to a compression for an ideal gas, it looks a lot like the regular pressure law, ideal gas law. So I get the change in the density. Okay, this again is not the density, this is the change in the density times Boltzmann constant times T, but then there's a factor multiplying it, which is gamma. And gamma is what's called the ratio of specific heats. What it does is accounts for this idea of injecting energy into the gas and changing its temperature. Okay, so the change in the total pressure given a certain starting point is given by the change in the density times gamma times T at the starting point. Okay. All right. And so with that, we know that the bulk modulus, okay, well, let me rewrite this one more time because we've been writing things in terms of mass density. So this is going to be gamma times the change in the mass density over the mass, okay, kBT. All right, so with that, I can write that my bulk modulus is the same as, remember the bulk modulus, there's a 1 over rho naught that comes in, so I have to multiply that here. So I have gamma rho naught kBT over the mass of the gas atom. Okay, and therefore the sound speed in an ideal gas can be written as this ratio of specific heats times kT over m. Okay, so now we have a sound speed that just depends on the temperature of the gas and also this ratio of specific heats. Okay, all right, let me stop there.